All right, let's get our detective hats on, because today we're investigating the very building blocks of our world. Our mission, should you choose to accept it, is to uncover the secret identities of two huge groups of elements, metals and nonmetals. So let's crack this case wide open. So every good investigation kicks off with a simple question, and ours is this. What is really the difference between something like a copper wire and, say, a lump of coal? I mean, sure, one's shiny and carries electricity, the other's dull and just crumbles. But why? What's going on at the most basic level? That's the core mystery we're here to solve.
To really get to the bottom of this, we first have to understand the biggest, most fundamental split in the entire world of elements. Pretty much every element you can name falls into one of two camps. This is where we line up our main groups of suspects, the metals and the nonmetals. Okay, so this right here, this gets to the absolute heart of the matter, the chemical motive of each group. See, at the atomic level, it all comes down to electrons. Metals, they're generous. They love to give away electrons, and when they do, they become positively charged ions, which we call cations. Nonmetals, on the other hand, well, they're takers. They're always looking to gain electrons, which makes them negatively charged anions. And believe it or not, this one little tendency, to give or to take, is the key that unlocks everything else.
Every good detective knows you can't just focus on motive. You have to look at the physical evidence. So let's head into our forensics lab and check out the distinct clues, the physical properties that help us tell a metal from a nonmetal, a lot of times just by looking at them. And here it is, our evidence locker. This table basically lays out all the classic tells for each group. You can see metals are usually shiny, hard, and you can reshape them. Nonmetals? Pretty much the opposite. Dull, soft, and if you try to reshape them, they break. Let's dig into a few of these clues a bit more closely. First up is luster. It's really just a fancy word for shininess. Metals, when they're in their pure state, have this incredible gleam, and it's all because of how their unique atomic structure bounces light around. And nonmetals, well, they're typically pretty dull. It's one of the fastest visual tests in our whole detective kit. Next, let's do a stress test. How do our suspects hold up under pressure? Metals are both malleable, which means you can hammer them into really thin sheets, and ductile, meaning you can stretch them into wires. This works because their atoms can literally slide past each other without the whole thing falling apart. Nonmetals, though, are brittle. You hit one with a hammer and it's not going to bend. It's just going to shatter into a million pieces. And if you want to know just how wild this ductility thing can get, check this out. Just 1 gram of gold, that's about the weight of a single paperclip, can be drawn out into a wire that's 2 kilometers long. I mean, that's just insane, right? It's a kind of superpower that only metals have. Okay, and finally, the energy test. This one is absolutely crucial. Metals are amazing conductors because they have this sea of electrons just floating around, ready to carry heat and electricity from one place to another. It's exactly why our electrical wires are made of copper. Nonmetals are the opposite. They're insulators. Their electrons are locked down tight, which is why the plastic coating on that same wire is what keeps you from getting a nasty shock. So, we've looked at the physical evidence, but now it's time to profile the chemical behavior of our metal suspects. Because here's the thing, not all metals act the same. Some are, well, let's just say they're a lot more reactive than others. And that brings us to a really important question for our investigation. I mean, with all these different metals, how do we keep them organized? How can we possibly predict which ones are going to react like crazy and which ones are more chill? We need a lineup. And here we have it, the reactivity series. This is the official police lineup for our metal suspects, all organized by how likely they are to react. Way up at the top, you've got the really reactive ones like potassium. We're talking explosive reactions. As you move down the list, that reactivity drops off, all the way to the super stable metals like gold and platinum at the bottom. This chart is absolutely key for predicting chemical reactions. Now, let's open up the next case file. What happens when these two totally different groups, our electron-giving metals and our electron-taking nonmetals, finally come face to face?
What happens is something called an ionic bond. Remember how metals make positive ions and nonmetals make negative ones? Well, an ionic bond is just the super powerful magnetic-like attraction between those opposite charges. It is the ultimate story of opposites attracting.
You can think of it like a little 2-step electron heist. Step 1, the metal atom just gives up its outer electron. Step 2,
The nonmetal atom swoops right in and snags it. And that simple transfer is what locks them together in a really strong ionic bond. Let's look at a classic case, table salt, or sodium chloride. You see here how the sodium atom hands over its one outer electron to the chlorine atom. That creates a positive sodium ion and a negative chloride ion. They snap together because of those opposite charges, and boom, case closed. We've just formed an ionic compound. So now that we get how metals behave, let's tackle a huge real-world problem. Most metals aren't just sitting around waiting for us. They're locked up inside minerals called ores. Our new job is to figure out how to bust them out of their mineral prisons.
This flowchart here is basically our master plan, and what you'll notice right away is that the strategy we use depends completely on where that metal is in the reactivity series we just looked at. The more reactive the metal, the harder it is to break it out. For the metals at the very top of that list, we're talking the high security suspects. We have to bring out the heavy machinery. They want to be in a compound so badly that you need a massive jolt of electricity and a process called electrolysis just to force them out of their molten ore. Now, for the metals in the middle of the pack, like iron or zinc, the job's a bit more standard. We can usually get them out by heating their oxides with carbon. The carbon basically comes in and steals the oxygen away, leaving us with the pure metal. And finally, we get to the easy score, the least reactive metals, the ones at the bottom, like gold and silver. They're not really interested in bonding with anything, and that means you can often find them just hanging out in their pure native state. They are by far the easiest to get your hands on. But listen, our investigation isn't over just because we got the metal. Now we have to protect it. There's a relentless enemy out there that's always trying to ruin our hard work, and its name is corrosion. That's right, the crime keeps going. For a metal like iron, as soon as it's exposed to air and water, this slow, destructive process kicks in. We have to stop the rust. So this is our protection plan. We can put up a simple barrier with some paint or oil. We can use a cool method called galvanization, where we coat the iron with a more reactive metal like zinc, which basically sacrifices itself. We can even change the metal's very nature by alloying it, mixing it with other elements like chromium to create something totally new, like rust-proof stainless steel. So, there you have it. We've identified our suspects, we've examined all the evidence, and we've learned how to protect our assets. You are now officially an element detective. So the question is, with these new skills, what other mysteries in the world around you are just waiting to be solved?